One of the things that I hope you notice as you take a look at these various rules is the similarities between them. Because yes, you've seen all of these rules for years, but have you ever noticed how the logarithm rules and the exponent rules are so closely related? Like for instance, up here, when I multiply, that becomes addition. Notice with the logarithms, when I multiply, it becomes addition. And the same thing happens with division to subtraction, and exponents, a power to a power, we end up multiplying them. Notice here with the exponent, it ends up multiplying. These rules are basically the same rules because logarithms are actually basically just exponents. And so a lot of the rules are the same. Now, one thing that you might not see a parallel for, though, is something like this. This is change of base formula if you wanted the actual name. So when you're asked to say, hey, what does this logarithm equal? Like what is log base 3 of 5 or whatever? This is what you use. Now notice I wrote two different things here. Log x over log b. That's using base 10 logarithms. Or ln x over ln b. That's the natural logarithms. So log base e, basically there. Technically, you could do the change of base formula like this. With any base, you could do log base 2 on both of them, or log base 3. But because these are the buttons on your calculator, log and natural log, those are the ones we tend to use. What I want you to see here is that you can use either one when doing the change of base formula to calculate a value. You could use log over log, or natural log over natural log. It just has to be the same one on the top as it is on the bottom. And then the other detail I haven't mentioned yet, notice over here, yes, you need to know these. This is the one that we just tend to easily forget, right? Anything to the power of 0 equals 1. We tend to forget that, so if you tend to forget it, it's just a refresher. But then I know from some recent assignments that we definitely get rusty on this one, right? The negative exponents. Basically, a negative exponent flips that in the fraction. And we're going to practice some of these ideas. So we're going to start with this problem. I'd like you please to simplify this. As you take a look at how you work through this problem, there's actually a couple different techniques that people use when doing this particular one, mainly centered around, do you simplify the stuff inside and then square it, or do you square everything and then simplify? And either way will work. So either way is valid. So I'll show you both methods. The first one, I will simplify inside first. So I'm just dealing with this part in here. So the 12 over 15. That works just like 12/15 as a fraction normally would. So I look to say, okay, well, what can I divide out of both of them to reduce the fraction? Divide them both by 3, so that becomes 4/5. Okay, so that's 4/5. I have an m to the 5th. And on the bottom, I have that a to the negative 7. Now what happens to the a to the negative 7? Yep, it flips into the top. And when it goes into the top, we consume the negative, basically. It becomes positive. And then on the bottom, the m to the 0. What does m to the 0 equal? 1. And so that just goes away. So all that's left on the bottom is just the 5. So we're going to do that squared. Now, we can go ahead and square it. Now in squaring the stuff inside the parentheses, basically you're squaring everything inside. So first thing I need to do is square the 4. 16. Square the m to the 5th. When we do a power to a power, we multiply those, so that is m to the 10th. Same thing with the a. 7 times 2 gives me 14. And then on the bottom, I square the 5 as well, so that becomes 25. Does that reduce any further?
Yes.
Doesn't look like it to me, because the 16 and the 25 share no factors other than 1. And then the m appears once and the a appears once. So that's as good as it gets. Yes, that is your final answer. All right, now I did mention that you could have done it the other order. You could have actually started by squaring. That would be fine. You would end up with 144 m to the 10th over 225 a to the negative 14 m to the 0. And then you'd have to work with it from there. In this case, and yes, it will reduce to be the same thing. But in this case, which one seems easier? To me, this route seems easier, but it's only because as I look at this problem and start saying, okay, what am I going to have to do? It's a lot easier to reduce 12/15 than it is to reduce 144 over 225. But otherwise, it's all about the same work. If we're going to simplify this, basically our goal is to turn this into just a single logarithm. Now the first thing I want to do whenever I'm doing that work is deal with anything that's out front. I want to deal with that 2 first. Notice the first logarithm doesn't have anything like that, so I'm going to just leave that as log base 3 of 5 minus. Now we have log base 3 of what? It's going to be 7 squared. Yes, because remember the number multiplied out front becomes an exponent, and 7 squared is 49.
Heck yeah.
All right.
I got it right.
So there's our first step, but we're not done yet because we can still simplify this further. Notice, and this is what allows us to simplify it further. If we don't recognize that this is because we can, we might make mistakes later. Both bases are the same. If one of those bases was different from the other one, we couldn't combine them. And so, I don't know if you actually thought that one through or not, but make sure that you are aware that it only works because they're the same. Now, that's going to give me log base 3 of, now the subtraction becomes division. Which number's on top, the 5 or the 49?
5.
The 5, yes, it comes first in subtraction, it comes first in the division. And so then this is now fully simplified. And so that's going to be our final answer, because we're just asked to simplify it. We weren't asked to go ahead and calculate it out. But we could probably still use some practice calculating them out, right? Okay, well then, let's actually evaluate a couple of them. And I'm going to take this one step further. Do these without your calculator. All right, now as you take a look at this, if we're going to do this without our calculator, we have to remember what log means. And just to illustrate how we know what it means, it's kind of like if I said log base 2 of 16 equals x. If I rewrote that as an exponential, it would be 2 to the power of x equals 16. So you'll notice that when I see log base 2 of 16, what it's really saying is 2 to the power of what equals 16. And so that's how we can know just by looking at it that the answer must be 4. Because 2 to the power of 4th is 16. Now could you do it on your calculator? Yes, you could. You could actually do log 16 divided by log 2, but it would give you the same thing. Now for the second one, okay, it's basically saying 4 to the power of what equals 1/16. Now if you don't know that one off the top of your head, instead, notice since it's 1/16, 4 to the power of what equals 16? 2. Okay. So how do I then make it 1/16? How do I flip that into the bottom of a fraction?
Negative.
Yep. We make the exponent negative. And so that's why the answer there is -2.
Negative.
All right, so now we're going to do that first problem. The natural log of 2x plus 3 equals the natural log of 53. Now, technically speaking, what I can do behind the scenes here is I can actually do e to the power of both sides. And that actually lets me do this technically speaking, but I don't even have to do that to both sides because, notice, it's the natural log of both sides. If the natural logs are going to be equal, then the stuff inside of them must be equal. And so since they are both just natural log of the side, it gives us that. Which, by the way, is the same thing you would get if you did e to the power of both sides. All right, so for that first one, we get x equals 25. Once we got rid of the natural logs, it was easy. Second problem now, how do we attack that one? Well, the first thing is I cannot immediately turn it into 18 minus 9 equals x. That is not going to work, because it's two separate logarithms on the left-hand side. If it were just a single logarithm on the left-hand side, we might be able to do it though. And notice we can do that. On the left-hand side, I can change that into log base 5 of what? It'd be 18 divided by 9, which is 2. And so, if log base 5 of 2 equals log base 5 of x, what does x equal?
2.
It's got to be 2. Technically, I'm doing 5 to the power of both sides. All right, so for doing that first one, I have two logarithms that are being added together. The first thing I want to do, anytime I see logarithms that are being added or subtracted, is I want to try to combine them into a single logarithm. So I'm going to do that first. So on the left-hand side, this is going to become log of, well, when I add the logarithms, what do I do with the stuff inside? I'm multiplying. So that means I have to multiply x by x, and I have to multiply the x by the 9. I have to distribute the x to both. And that is going to then equal 1. Okay, but now I have a log equals just a number. It's not log equals log this time. Well, in this kind of a case, when you just have log equals number, change it into exponential form. All right, and so then our base of our logarithm, remember it's not written in, so it's 10. So this is going to be 10 to the power of 1 equals whatever's inside the logarithm, the x squared minus 9x. So that's just using the same rule of converting between exponential and logarithmic forms. And so if I have 10 to the 1 equals x squared minus 9x, I got x squared and I got an x, I got a quadratic. I'm going to solve it by setting it equal to 0 then. So that means subtract the 10 from both sides. I have x squared minus 9x minus 10. I need to solve it. My preferred method for solving is factoring. Can I factor this?
Yes.
Yes, and thank goodness. Because if we couldn't factor it, we'd quadratic formula. So thank goodness we can factor it, right? And so 0 equals then, if I factor it, x minus 10, x plus 10, I'm sorry, x plus 1. And so then we can find out that here x equals 10 or negative 1. Kind of. We just ended up with multiple solutions. What do we normally have to do when we end up with multiple solutions?
Plug 'em in.
Check them.
Oh,
Now, I'll tell you, one of them works and one of them doesn't in this case. Can you tell, knowing that, which one does not work?
-1.
Yeah, the negative. Because remember, we cannot take the logarithm of a negative. And if I plug negative 1 in for x here, log of negative 1 is not going to work. So we finally end up with an answer of just x equals 10. All right, now on to the second problem. And on this second problem, there's two different ways you can do this. And it's kind of the algorithmic approach versus the instinctual approach. Okay? The algorithmic approach is I start with an exponential, so I'm going to turn it into a logarithm. And so I'd write it as log base 8 of 64 equals 6x plus 1. And I can solve that because log base 8 of 64, that's 8 to the power of what? Equals 64. That's a nice pretty whole number. It's got to be 2 because 8 squared is 64. And so then we can just solve it from there, and you end up with x equals 1/6 by the time we've done all the work. Now, I said there's also another way, the instinctual approach. You might have recognized, hey, I can rewrite both of these as a base 8 exponential, because that 64 is 8 squared. So I could start by writing it like that, because if I do that, then I can just say, hey, the bases are the same, so in order for them to be equal, the exponents have to be the same. And solve it through the same way. Either way, x equals 1/6. All right, so the first thing we want to do, fairly easy and straightforward, I hope, is we move that 5 over to the other side. So I add 5 to both sides. But now I have an exponential. And just like the last time when I had an exponential, one way to go about it is to turn it into a logarithm. In fact, that's pretty much our only way here. Now, when I turn it into a logarithm, though, I do not want to write log base e, because that's quite a bit more work to type in our calculator and work with. Remember that log base e is the same as natural log. So this becomes the natural log of 23 equals, always equals the exponent, so it equals the 2x plus 1. Now, natural log of 23. Is that one you can know off the top of your head? No, definitely not. And so, that's where you got to break out your calculator to finish this problem off. Go ahead and do so. And so when we do that calculation, then subtract the 1, then divide by 2, we end up with an answer of about 1.07. So now, we move that 4 over to the other side. Now I just have log equals, so that's where we turn into an exponential. So 2 to the 5th equals x minus 3. 2 to the 5th, you know that one off the top of your head, right?